Hello everyone. So today we are going to look into the current application of the DL configuration. Okay, as I told you in the previous video that DL configuration was a very old methodology of giving configuration to stereoisomers, and now it is kind of limited to only the carbohydrates as well as the amino acids. Okay, so if you remember from the previous discussion that we did, the DL configuration is basically a synthetic correlation with the standard D or L glyceraldehyde. Okay, so since it is a comparison between the compound, it's a synthetic comparison between the compound and the DL glyceraldehyde. It is a relative configuration. It is a relative configuration. Okay, so when the absolute configuration of the compounds we started to understand, like after the X-ray crystallography came into picture, we were able to identify the configuration at each stereo center of the stereoisomer, and therefore we were able to know the absolute configuration at each and every stereo center. Okay, so now after knowing the absolute configuration, now we apply DNL configuration on the basis of structural correlation. Okay, so now the correlation that we do is not synthetic correlation, but rather a structural correlation. Okay, and for that correlation, we use the planar formula of stereoisomer, which we now know as the Fischer projection formula. So that is what we use in order to do the structural correlation with the D and L glyceraldehyde. Okay, so this structural correlation will give us an idea whether structurally they are related to D-glyceraldehyde or they are structurally related to L-glyceraldehyde. So very important thing you must note is that when we assign the D or L configuration, now we use the Fischer projection formula. So I hope when you're watching this video, you have a brief idea about what Fischer projection is and how it is actually drawn. So when we are going to use the DL system, the DL configuration, we need to write the Fischer projection formula in a particular way. So we need to understand the method of writing the Fischer projection formula so that we can compare structurally it with the glyceraldehyde and thereby assign the corresponding D and L configuration. So how should we write the Fischer projection formula? First important point that you see is that the parent carbon chain is drawn on the vertical bond. So as you know, Fischer projection has the horizontal bond and the vertical bonds. Okay, so on the vertical bond, we draw the parent carbon chain. Okay, so organic molecule has a parent carbon chain. So that parent carbon chain is drawn on the vertical bond of the Fischer projection. Okay, second point is the substituents are drawn on the horizontal bond. Okay, so the substituents that are coming on each of the carbon atom is drawn on the horizontal bond. The third point is how you should arrange the parent carbon chain. So when you write it on the vertical bond, the first priority carbon should be written on the top of the vertical bond. Okay, or some of the textbooks use like most oxidized carbon should be written on the top and the rest of the carbon chain as under. Okay, so this three key points. These three key points you should understand in order to write the correct D and L configuration. Okay, so let's try to first understand the glyceraldehyde, and then probably we will apply to higher monosaccharides. Okay, so if we look here in this particular figure, this is the Fischer projection for the glyceraldehyde. So the parent carbon chain, as you can see, if I number it, 1, 2, and 3. So this is the parent carbon chain. So I have correctly placed the parent carbon chain. I've correctly placed the parent carbon chain on the vertical bond, and the first priority carbon I have placed on the top, or the most oxidized carbon. The first priority carbon is also the most oxidized carbon. That also is on, according to that also, it is on the top of the vertical bond. Okay, so once I write like this, the substituent, in this case, I have the hydroxy group as the substituent, that is placed on the horizontal bond. Okay, now when my OH is on the right side, okay, when the OH group is on the right side, I know from our previous discussion, you know that that particular configuration would be called the D-glyceraldehyde. Okay. Similarly, when the OH group is on the left side of the Fischer projection, when you write it in this particular format, this would be your L-glyceraldehyde. So, so this is the formula for the glyceraldehyde. Very good. So similarly, this is the formula for the L-glyceraldehyde. So this is the formula for the L-glyceraldehyde. This is the formula for the D-glyceraldehyde. Now let us try to apply try to understand these, how we structurally correlate the other monosaccharides. So this is the simplest aldose sugar. It is a triose. Okay, so it is a triose, and it's the simplest what you say, the aldose sugar. Okay, now let us look at the higher version, that is the Tetros. Okay, so here in the simplest version we have only one chiral center. So the next higher version would be having two chiral centers. So that is what we write here as the Tetros. This is known as the Tetros. Okay, so Tetros, what you see here, we have now two chiral centers. Okay, basically, if you see here, the carbon chain is written on the vertical chain. Okay, and the most oxidized carbon is placed on the top. Okay, so if you compare the Tetros with glyceraldehyde, the basic structural correlation is the same. You have the aldehyde, and the below you have the CH2OH. Okay, so similarly here you have the CHO and the CH2OH. So this is the higher version of the aldose. Okay, now the difference would be coming in these chiral centers. Okay, difference would be coming in these chiral centers. So that is what we are going to understand. Okay, now a basic stereochemistry. Since we have two chiral centers present, how many stereoisomers you expect? You expect 4 stereoisomers. You expect 4 stereoisomers. Okay, so two of them I'm going to draw here because two possibilities are possible. Okay, for example, I'm keeping so if I try to compare, so let me show you here. If I try to compare this part, this is the part that is going to decide, because this is what is similar to the glyceraldehyde part, and the configuration or the presence of the OH group in this part would decide whether it belongs to the D configuration or it belongs to the L configuration. Okay, so initially, or right now, I'm going to use the D configuration. The L configurations would be simply the mirror image of the D configuration. And why I'm drawing the D configuration is because D configuration is the one that is the abundant form, that is the natural form of the monosaccharides, are the D form. So L form is just the mirror image, so you don't have to worry. So once you know the D form of a particular sugar molecule, the L form is pretty easily understood. Okay, so right now I'm going to put this is tetros sugar. So we should have a total of 4 tetros sugar. Okay, so let me write the 2 isomers with the lowest most chiral center with the OH group on the right side. So in this both case, you see the OH group is on the right side. So that itself tells that both these configuration that I'm going to write would be a deconfigured tetros sugar. It would be a deconfigured tetros sugar. So now we have this particular chiral center here. Here we have H and OH that could be written in 2 possible ways. Okay, so what are the 2 possible ways? One in which this can be written simply as H and OH. The other possibility is simply OH and H. These are the only 2 possibilities you can draw for this particular chiral center. Okay, very well said. So what you see here is in one case you have 2 similar groups are on the same side. Okay, and the other case you see the similar groups are on the opposite side of the Fischer projection formula. Okay, so if you remember, you might have learned about erythro and trio. That particular thing, that nomenclature is coming from this sugar representation, that is the tetros sugar. Okay, so whenever you have the OH group or the similar groups on the same side, we call it as erythro. And in this case, this is a aldose sugar, and this is nothing but your erythros. This is your erythrose sugar, and this would be your threose sugar. This would be your threose sugar. And from this particular term, what you get your erythro and the threo form. Okay, so whenever you have 2 chiral centers present in a stereo isomer, and you see that the substituents are of similar substituents are on the same side, we say that is a erythroisomer. Okay, and when you see that same substituents are on the opposite side, we say them as the threo isomer. Okay, so that particular erythro and threo has come from this representation of the tetros sugar. Okay, so this is the D form. There are 2 D forms present. So obviously the L3Os would be simply the mirror image of this particular configuration would be L3Os, and the mirror image of this particular configuration would be your L3Os. Okay, mirror image of this one would be L erythros. The mirror image of this particular Fischer projection would be your L3Os. Okay, so very well said. Now let us go to the, so that takes care of the 4 isomers. Okay, 2 are D form, 2 are L form. So that's why you have 4 isomers. Let now go to the another higher form where you have 3 chiral centers. Okay, so this would be your pentose sugar. So this is your pentose sugar. Now let's again calculate the number of stereoisomers possible. So you have 2 to the power of 3. So it should be 8 stereoisomers you should get. Okay, 4 would be D form, 4 of them would be D form, 4 of them would be the mirror image, that is the L form. Okay, so right now I'm going to concentrate only on the D form. So that means the lower part, because this particular part is the one that is similar to your glyceraldehyde part. Okay, so I'll keep the OH on the right, because then those sugar molecules would be called as the D form. Okay, so I'll keep in this all four of them. I'll keep the H and OH on the in this particular way, so that the OH is on the right side. So when OH is on the right side, all this would be deconfigured. All of them would be D. Okay. Now the difference comes in the configuration of the others. Okay. One of them would be simply every one would be having the OH on the other two would be having the OH on the same side. The other extreme can be both the OH would be on the opposite side. Okay, so this would be nothing but keeping this particular chiral center constant. You can write HOH, this keeping the constant. You change the second one. So if I write it as 1, 2, 3, 4, and 5, you change the second one as OH and H. Fine. Now, another stereoisomers would be simply what? You keep this first one constant and change here. So this becomes OH and H. Okay, so these are the three forms. This one in which all the OH group, okay, all the OH group when they are on the right side, that would be that you call it as ribose. All right. Ribose is a very common sugar which you find in RNA. Okay. Okay. So ribose. Okay. Ribose. So you can remember like all right. So when all the OH group is on the right side, we say it as ribose. So when you see C2, when C2 carbon has the OH inversed, okay, changed, we call it as arabinose. So this is nothing but your arabinose. Okay, so you don't have to remember all these things, I guess, because sometimes the most common ones are the one that you need to remember, like ribose, glucose, fructose, galactose, mannose. Okay, these are the few things you should remember. Otherwise, you don't have to remember all of it. Okay, usually for the Indian universities, you just need to remember these because they expect you to know, because they are very common monosaccharides that you find in many of the glucose molecule. So that's why you should remember that. Okay, so ribose, it's pretty simple to, I hope you understood that it's simply all right. When you see ribose, all right, that means all the OH group is on the right side. Okay, so whenever you see that, it means that pentose sugar is ribose. So why it is called pentose? Because you have 5 carbon atom. That is why it's called pentose. This is called tetros because it has 4 carbon atom. Okay. So let's look at the other name. So this one, the extreme one, is nothing but your lysose. You don't have to remember. I guess these structures won't be asked. Usually doesn't come in the question papers. Okay, you just have to remember, know about it. Okay, so this is xylose. This is xylose. Okay, xylose, and this is lysose. Okay, so all this that we have drawn just now are the D form. Okay, because the lower part, which is similar to the glyceraldehyde part, is having the OH on the right side. Okay, that's why all these are the D form. So since we have 8 stereoisomers, 4 of them are D form. The L form is simply the mirror image. So if you draw the mirror image of D lysose, it would be L lysose. So mirror image, if you draw, you know that the OH would come on the left side. So that means that's why it says L lysose. Okay, so that's how you can easily do the thing. Okay, now let us go to the final version and more higher version of the sugar molecule. So here you have the hexose sugar. Okay, hexose sugar are very, very important because they make up most of the carbohydrates, the polysaccharides that you see in the carbohydrate chemistry. Okay, so how many stereocenters are here? 4 stereocenters. So how many stereoisomers are possible? 16. Okay, now you would be pretty easy to easily say that 8 forms would be D and the mirror images of 8 forms would be L. So we will concentrate on D form because all the natural monosaccharides, they are the D form. Okay, so we will concentrate only on the D form because D form, once you know it, L form is simply the mirror image of that. Okay, so I'll draw the, all of them would be D form. So the lowest chiral center, okay, or lowest stereo center, that is more appropriate terminology to use nowadays. Lowest stereo center would be having the OH on the right side. That is what you have to remember. So that configuration is what going to decide whether it would be a D or a L configuration. Okay, so all this would be D. Okay, I'll just write simply D. That means all these hexose sugar that I'm going to draw is having D. Okay, so one possible way of writing the other 3 chiral center is simply same way as the highest chiral center, highest numbered chiral center. Okay, perfectly fine. And the other extreme would be all the 3 having OH on the left side. That means these are all H. Perfectly fine. Now, let us do the same way as we did for the pentose sugar. So what you do, keep these 2, okay, these 2 constant. Change the upper one. So it would become OH, H. Okay. Similarly, when you do here, next change the 1, 2, 3. Third carbon you change. So it becomes OH, H here. Rest of them you keep it like this, H and OH, and then H and OH here. Okay. Now in the final part, keep the others constant, that is the second and the third carbon constant. Change the fourth carbon, OH and H. Okay, so this is the 3 different possibilities you see here. Now these you can draw with respect to this also. Okay, so what you can do, so here again there is a lot of all the 3 are have the OH on the left side. Okay, so keep the this third and fourth carbon constant. So OH is constant here, and change the first carbon. So this is the first possibility. Second possibility you can draw is keep this constant and change the third carbon to H and OH and this constant. Okay, last possibility is keeping the second and third constant, second and third carbon configuration constant, and change this one, H and OH. So if you look now, all of them are pretty different. They are all diastereomers. They are all diastereomers. Not single of them are same. Okay. So now we need to identify. So what you see in all this case, the part that decides the DL configuration, that is the what you say, the lowest chiral center, or you can say the highest numbered chiral center. So why I'm saying highest numbered, because if you number these carbon chain 1, 2, 3, 4, and 5, and 6. So the chiral center with the highest number is this chiral center. So that is why this chiral center is what going to decide whether it would be having a D configuration or it would be having a L configuration. So what I have drawn just now is all D form. Okay, now we have to identify which is glucose. So glucose is the one that you should always remember. So glucose, if you see, it is HOH, OHH, HOH, HOH. So this one is what you call as glucose. Okay, so you can easily remember this. You have to remember this. I have seen one example which teaches good manners. Like if you talk about this OH and H, so it's like never show this kind of way of showing the fingers. Okay, it's not a good way of showing the fingers. So that kind of notation I have seen in one of the videos one of the teachers was using. So this way you can remember. So some good manners. So glucose teaches you some good manners, that you should never show any kind of fingers to anyone. So that kind of thing you can one way remember. Another very important thing that you can remember is the this manus. Okay, manus is something like holding a gun. Okay, so if you hold a gun, something like this, so it's like a gun. So man, gun man. So that way you can remember this structure. So this is for the manus. Okay, this is the manus structure. Then another structure that you can think of is this one. This particular isomer, if you see, it is something like glucose in an inverted way. If you invert this molecule, okay, you will see this particular OH coming here, and rest of them is having the same OH on the right side. Only this particular chain has been interchanged. Okay, so this particular is called glucose. So it is kind of an inverted glucose you can talk of. Okay. Now galactose. So galactose is nothing but a C4. It's a 1, 2, 3, 4. So it's a C4 epimer. Okay. C4 epimer of glucose. So if you know the structure of glucose, it's an epimer. Now what is an epimer? Epimer is that isomer which differ at only one chiral center. So if you compare glucose and this is the galactose. So let me write the galactose first. Okay, galactose. So galactose and glucose, if you compare the galactose and the glucose, what you see is you find only the difference in this chiral center, that is the fourth chiral center. Okay, so fourth chiral center, you see a difference, that is the OH has now come on the left side. So it is a C4 epimer. So because 1, 2, 3, 4. Okay, so it's a C4 epimer. C4 epimer, and that is why if you can remember galactose as a C4 epimer. Okay, so these are the most common ones that you should remember. Okay, rest of them I can give you what the name of. When all is on the right side, it is called aldose. Okay, when one of them, that is a C2 epimer, it's a epimer, it's only differing at this. So C2 epimer of aldose would be called as altrose. Altrose. That means the altrose is simply differing only at this C2 chiral center. So that only is differing. So it is a C2 epimer of allose. Okay, so that is altrose. So glucose, you know, glucose, you know. Now this one in which you have this particular, this is called idose. Okay, even I don't remember it, so I don't expect you to remember it also. So this is nothing but idose. This particular configuration is Idose. Okay. Usually these kind of things you are not asked because they are not very common kind of sugar that you find. And this last one is the talose. Okay, so I hope you got a brief idea how to. So here it's all D. So this is D-allose, D-altrose, D-glucose, D-gullose, mannose, idose, then galactose and talose. All are D form. Simply the mirror image of all these would give you the 8L form of the hexose sugar. Okay, so these are the way in which you make the various D or D form or L form of the various monosaccharides. So how you decide whether it's a D or L form, you will look at this penultimate chiral center. Another terminology that some of the book uses, penultimate chiral center. That means chiral center that is before the ultimate, penultimate. So penultimate chiral center. So because when you number it, 1, 2, 3, 4, 5. Okay, so fifth carbon is the ultimate carbon. So penultimate. So before the fifth carbon, the chiral center which is there, that decides the D and L configuration. Or another books, some books talks of the highest numbered chiral center. So this particular chiral center that I have just now boxed, okay, that particular chiral center is the highest number, that is 4. The number that you get is 4 in the circle that in the pentose sugar that I have drawn now. So that is the highest numbered chiral. So in that is going to decide the configuration of the D and L configuration of the sugar molecules. I hope you understood how we decide the sugar configuration. So now what you see here is we are doing a kind of relative correlation. So structural correlation. We are not doing any synthetic correlation because now we know the absolute configuration of every stereo center in a monosaccharide. So we don't need to synthetically prove any stereo center. But now, since we had been using D and L quite a lot in the old for the sugar molecules, that's why we still keep it for the sugar molecules, because we know the absolute configuration of the sugar molecules and we know them, that when we say glucose, all this configuration would be like this. When we say galactose, its configuration at each stereo centers we are knowing. Okay, so how to differentiate two different forms of glucose? Okay, it's simply on the basis of the D and L configuration. That means when you have the glucose where the lowest or penultimate carbon, or we say highest numbered carbon atom, has OH on the right side, as you see in the D-glyceraldehyde, then we say that is having the configuration of D. Okay, and when the OH is on the left side, okay, of the Fischer projection formula, we will say that it is having a configuration of capital L. So I hope you understood. We are doing only structural correlation with the D-glyceraldehyde. Nowadays, we don't synthetically correlate anything with D-glyceraldehyde because it leads to a lot of ambiguity or confusion, which we looked in the previous video. Okay, so this is how we structurally correlate. So remember an important point which I already taught you, that when you are using the the D and L configuration, whenever you are using the D and L configuration, it is important that you represent the molecule in the Fischer projection formula. That is very, very important. Otherwise, you might get wrong. If suppose you are given the wedge-dash formula and you are asked to predict the D and L configuration, please convert first that into a Fischer projection and then decide the D and L configuration. Otherwise, you might get wrong. Okay? Because when you write the Fischer projection formula, you should remember to write the Fischer projection formula in this particular aspect. Okay, so when you write it in this aspect, you will be able to correctly decide whether the given molecule is D or a L configuration. So I'll do one more video of this where I'll be talking about how to convert a wedge-dash formula into a Fischer projection formula. I will not be going into the details, but I'll show you that how it is important to draw the representation in the Fischer projection formula in order to correctly decipher the D and L configuration. So thank you very much for your attention. Have a nice day.